Welcome to the debate. Today we are tackling a really fundamental conflict in modern software architecture. And it's not about, specific languages or shiny new frameworks. It's actually rooted in physics and economics. This massive and frankly widening performance gap between the CPU and main memory, what everyone calls the von Neumann bottleneck.
Right. And Gap almost undersells it. It's catastrophic from the CPU's point of view. We're talking about a situation where a modern CPU can zip through an instruction in maybe a few cycles, but then it hits a wall. It can stall for, hundreds, sometimes over 350 cycles, just waiting for data to crawl in from RAM. That's basically an ice age in machine time.
Precisely. And just to put that into context, right, the L1 cache, that's the CPU's super-fast local memory, accessing that might cost, say, 4 cycles. Waiting 350 cycles for main memory, that's essentially slamming the brakes on computation. The whole memory hierarchy, L1, L2, L3, it's all built to try and guess what data the CPU needs next, exploiting locality by moving data in those 64-byte chunks, the cache lines. So yeah, data latency, not how fast we can compute, that's the real bottleneck in pretty much any complex system today.
Agreed. Yeah, the bottleneck is absolutely data access.
So the core question for software architects right now, I think, is this. Should we be prioritizing what's called mechanical sympathy, designing our code to inherently respect this hardware reality, which pretty much inevitably leads us towards data-oriented design, or DoD, or does object-oriented programming's sort of traditional strength in modeling logical complexity still justify it being the dominant architectural choice? My position is that the empirical performance data, it's overwhelming. It dictates a foundational shift to DoD, at least for anything performance critical.
I see it, a bit differently. While I absolutely acknowledge you can't deny the raw throughput advantage of DoD and those really specific calculation-heavy hot paths, I'd argue that OOP's fundamental value in managing overall system complexity and frankly, developer cognition, how easily we can actually reason about and maintain a system, means it still holds its primary relevance. The issue, I think, often isn't OOP itself, but maybe how it's sometimes misapplied or poorly implemented.
That relevance, though, I believe it's fading, crushed under the weight of hardware reality. My core thesis here is that OOP's abstraction away from the physical hardware, it's become a demonstrably leaky abstraction. It imposes this growing and often just catastrophic performance tax. DoD, on the other hand, aligns the design with the hardware reality, specifically by championing the structure of arrays, or SOA, memory layout.
Right, the SOA layout. And that's a perfect example, isn't it, of trading perhaps developer intuition for raw machine efficiency. Because in traditional OOP, we tend to use the array of structures, AOS layout, which, let's face it, is intuitive. You have an array of things, like player objects, where all the data for player A is grouped together, then all data for player B, and so on.
And that's exactly the problem from the CPU's perspective. DoD flips that entirely. In SOA, instead of grouping data by the conceptual thing, you separate data by its type. So if you've got positions and velocities, all the positions are packed tightly together in one contiguous array, and all the velocities are in a second contiguous array.
And in doing so, you decouple the conceptual entity, the player, from its physical memory representation. Now, that is a significant cognitive leap for a lot of developers who've been trained for years to think of a player as this single encapsulated unit. You're essentially asking us to optimize primarily for the machine's cache lines, not necessarily for human understandable domain models first.
We have to, because that contiguous layout results in predictable, sequential memory access patterns, and that maximizes cache hits. This isn't just theory. This empirical alignment gives real, measurable results. Studies have shown DoD systems hitting performance gains ranging from 5x to over 13x. Specifically, in multi-threaded game simulations, we're seeing speedups up to 13.25x, and crucially, cache miss rates that are like 5.57 times lower than typical OOP counterparts.
When the main goal of your system is transforming data efficiently, the code structure simply has to be secondary to the data layout. Okay, look, I'm not going to stand here and question a 13x speedup in a, perfectly tuned data-heavy simulation environment. That's impressive. But performance isn't the only metric we care about, right? I maintain that OOP often remains the superior paradigm for managing the overall system complexity, developer understanding, and long-term maintainability, especially in large, long-lived applications, which, let's be honest, is where most software development effort actually goes.
I see why you emphasize maintainability, I do, but that very emphasis on human cognition comes at a direct and increasingly severe cost in machine efficiency, specifically through two fundamental hardware penalties that OOP almost by its nature tends to promote. The first big one is indirection. Think pointer chasing and virtual functions.
Well, the concept of indirection, while it does have a cost, is also the very foundation of architectural flexibility and rich domain modeling. It lets us create complex relationships between objects without locking them into rigid couplings.
But that flexibility is becoming prohibitively expensive. When an array of structures ends up being implemented as a collection of pointers to objects scattered all over the heap, which happens all the time with dynamic allocation, the CPU is forced into this nightmare called pointer chasing. It reads a pointer, waits for memory, reads the object data, which contains another pointer, waits again. Since those objects are scattered randomly, each jump, each dereference is highly likely to trigger a cache miss, forcing that painful 100 to 350 cycle stall we talked about. The CPU's prediction mechanism, the prefetcher, it's rendered completely useless because the memory access pattern is effectively random noise.
Okay, that's definitely a significant problem with dynamic allocation and scattered memory and performance critical loops. But let's also talk about the vtable penalty you mentioned. Polymorphism achieved via virtual function tables. Yes, it adds a mandatory memory indirection for every single virtual call because the actual function address isn't known until runtime.
Exactly. And that indirection doesn't just cost a memory lookup. It actively prevents crucial compiler optimizations, like function inlining. You're paying a performance tax simply to get runtime substitutability.
But that tax, I'd argue, is often an intentional strategic trade-off, particularly in systems where extensibility and dynamic behavior are genuinely paramount. Polymorphism allows for systems that are flexible, open to extension. You can add new types, new behaviors without ripping apart the central consuming code. Think about enterprise software where business rules change constantly. This flexibility is often a massive win for architectural stability and development speed, easily offsetting the loss of, a few nanoseconds on a virtual call in many contexts.
But that overhead adds up incredibly fast when you're processing not one, but thousands or millions of entities per frame or per transaction. And the problems go beyond just simple indirection. Let's talk about memory footprint and just plain data scattering. The sort of natural tendency in OOP development sometimes is towards the God object, or just large classes that accumulate more and more variables over time. This directly exacerbates cache pollution.
Now, that accumulation, the God object, I have to push back slightly. That's widely recognized as an anti-pattern, not an inherent failing of core OOP principles like encapsulation. Encapsulation is actually designed to protect data integrity, like making sure a bank account object's balance can only be modified through controlled methods. The solution there is better design, more focused classes, not necessarily throwing out the entire paradigm.
But the AOS mindset makes this kind of poor design the path of least resistance, doesn't it? Adding a new piece of data often means just chucking another member variable into the existing class definition. And this leads us straight into the second major architectural flaw I see: cache line pollution. This happens even when your OOP objects are technically contiguous in an array.
You're referring to the issue where the 64-byte cache line pulls in a bunch of data that isn't actually needed for the specific operation you're doing right now.
Precisely. Let's go back to that GameObject update example. Imagine you have a function that just needs to update the position and velocity for thousands of game entities, a pure physics calculation. In the typical OOP way, when the CPU needs to access the object's position data, the hardware dutifully loads the entire 64-byte cache line containing that object's memory.
And because of how the object is structured, that cache line inevitably drags in potentially irrelevant data, Maybe the sprite ID, the current health score, the character's name string pointer. Data that is completely useless for the physics calculation currently happening.
Exactly. It pollutes the extremely valuable tiny and fast L1 cache. It kicks out other useful data or even instructions that the CPU did need. It's just a tremendous waste of the most precious resource on the chip. DoD avoids this completely through what you could call system-level granularity.
Because in DoD, the physics system processes, say, the position array for all entities, and only the position array gets pulled into the cache. The health array, the sprite ID array, they're never even touched, so they don't pollute the cache during that specific physics update stage.
Correct. The cache stays laser-focused, filled only with the data and instructions relevant to the immediate transformation task. That is mechanical sympathy in action. We're ensuring the CPU works on these nice, contiguous, relevant blocks of data, maximizing spatial locality. It's a fundamental efficiency gain that OOP structurally tends to fight against.
Okay, I absolutely understand the efficiency gains there, especially for those bulk transformation tasks like physics or maybe rendering. But DoD arguably shifts complexity. It moves it away from localized object interactions and pushes it into the design of the overall data transformation pipeline itself. In OOP, adding, say, a new state variable to an entity might just be a single change within a class definition. In DoD, adding a new component type might require modifying multiple processing systems or creating entirely new component arrays, which significantly complicates managing the explicit data flow. It demands a much deeper, more holistic understanding of the entire system's pipeline right from the start.
But that upfront complexity, I'd argue, is a necessary investment if your system has any aspiration to scale effectively. And when we talk about scaling today, we're really not just talking about single-core speed anymore. We're talking about the absolute imperative of parallelism and exploiting SIMD single instruction multiple data. Remember that 13.25x multi-threaded speedup I mentioned earlier?
That speedup is compelling, yes.
And it's entirely predicated on the architecture. DoD's strict separation of data, the component arrays, and logic, the systems that operate on them, makes it what's often called embarrassingly parallel. Different systems or even different threads within a system can operate on independent component arrays simultaneously without the nightmare of complex, error-prone, shared mutable state management that constantly plagues large OOP systems when you try to introduce concurrency. OOP's reliance on locking, mutexes, synchronized access, it just kills parallel performance gains very quickly.
I absolutely concede the parallelism advantage. It's undeniable that DoD's structure, especially that SOA layout, is uniquely suited for SIMD vectorization too. Allowing a single instruction to process multiple data elements at once, say, crunching 4 or 8 positions simultaneously, which gives you those huge multiplicative throughput boosts. But I'm still not entirely convinced by the line of reasoning that dictates this specific architecture for everything under the sun.
Why not? Future performance gains are almost entirely dependent on multi-core scaling now. If your fundamental architecture is hostile to easy, safe parallelism, you are essentially building systems with a built-in hard performance ceiling.
That level of optimization, that focus on SIMD and massive parallelism, it feels like a highly specific technical requirement, primarily confined to what you called data-intensive domains. Game development, maybe complex financial modeling, scientific computing. For many, many other non-critical subsystems, think about the UI layer of an application, or the high-level application state management, or even complex enterprise business roles that might involve only a few entities but have intricate logic. Does the architectural overhead and complexity of implementing a full DoD or entity component system framework purely to gain parallelization capability that might never be fully stressed or needed really justify the added development friction?
Well, that friction, I think, is decreasing as the architecture matures and tooling improves. And the industry is already shifting, moving it beyond just a niche technique. Look at frameworks like Unity's dots or features being baked into Unreal Engine.
They clearly show that DoD and ECS principles are rapidly becoming standard practice, at least for managing entity behavior in high-performance contexts.
And okay, that brings us nicely to the pragmatic reality, which is often the hybrid approach. You sometimes characterize this compromise, an OOP shell managing a DoD core, as if it's proof that OOP somehow failed.
Well, isn't it often evidence of exactly that? The initial OOP framework delivered inadequate performance in the critical hot paths, forcing the developers to go back and refactor the core data management using DoD principles just to make the system usable.
I'm sorry, but I just don't buy that it's automatically a failure. That hybrid approach often represents the conclusion of a very sensible strategic design exercise. I mean, even the source material we looked at explicitly states the choice should be driven by the constraints of each subsystem. It favors OOP where logical complexity and human-centric modeling are the primary concerns, like managing UI state, handling user interactions, coordinating high-level application flow, and it mandates DoD only where performance constraints are severe and unavoidable. It's about using the right tool for the right job. Why would you mandate the inherent complexity of data-oriented transformations on parts of a system where performance is measured in, say, milliseconds responsiveness to a user click, not nanoseconds in a simulation loop?
Because the undeniable physical realities of the memory hierarchy mean that any system aspiring to true efficiency and scale must adopt mechanical sympathy as a core guiding principle. I believe that ignoring data layout in modern computing is fundamentally an architectural failure, because even seemingly minor optimizations at the data level accumulate massively under load. The empirical evidence we discussed, the 6 to 13x speedups, that's not marginal. That defines entirely different classes of performance capability.
I respect the empirical data, I really do. But OOP's proven strength in optimizing for human cognition, its established role in managing logical complexity and state transitions, ensures it remains a necessary, powerful, and often, yes, superior tool for large parts of many systems, specifically where the core challenge lies in varied behaviors and complex interactions, rather than just bulk number crunching. We simply cannot afford to sacrifice clarity and maintainability across the board for speedups in domains that don't actually demand them.
I still maintain that the definition of marginal is rapidly shrinking in the face of hardware trends. But I suppose we can agree that the truly sophisticated architecture, moving forward, is likely the one that learns to leverage both philosophies strategically.
Absolutely. I think it confirms that both paradigms offer distinct, very powerful advantages, and the future of successful, high-performance software almost certainly lies in the judicious and thoughtful application of both logical abstraction and hardware-aware data flow efficiency. Finding that right balance is key.